Hey, it's Jag. I've been rethinking the project.
Yeah.
A traditional style power supply, typically consists of a bulky transformer plus the rectifier and filtering circuit and all of that stuff. This takes up a lot of space. It's bulky, adds weight, and can be very expensive. Well, that's part of the charm and mojo of a big tube amp. It seems a little bit big and clunky for a single tube preamp. So I've been kind of looking at other options. What caused me really to think about this and look for a different way to power this project was when I was working with the strip lights and sourcing the switch mode power supply for it and all of that. I was thinking, oh great, more stuff to stuff in the chassis. That's one of the reasons I went to a bigger chassis. I also have been concerned about AC-induced hum in the filaments. So I was thinking about maybe building a DC heater supply as well. Even more stuff to shove in the chassis. I started thinking maybe I can do something different. While I was sourcing the switch mode power supply for the DC edge lighting strip, I noted that a lot of those strip lights, some of them are 5 volt DC, some are 12 volt DC, and some are 24 volt DC. Some LED strips are powered by 12 volt DC. The 12 and 12AX7 is 12 for 12 volt, and I can get a switch mode power supply with a 12 volt DC output. So I could run my edge lights off of that, and I could run my heaters off of that. I had never thought of this before. Keep in mind, I'm old school. I don't do this for a living, so I'm able to sort of keep my focus just on the things that I'm interested in, and I'd never really looked beyond the traditional way of building a power supply for a tube amp. I'm not particularly interested in solid state devices, should we say, but I'm developing an interest because there are lots of things we can do. I started wondering, can I use a switch mode power supply for this preamp project? Hello, YouTube. Yes, you can. It's totally doable. There are a fair number of people with videos on YouTube who have built not only preamplifiers, but full-blown amplifiers, and even audiophile enthusiasts have built preamplifiers and audio amplifiers using switch mode power supplies. Awesome. Not only that, I was reminded of something called a boost converter, which is a class of switch mode power supply that takes a DC voltage and steps it up to a higher voltage. So let's talk about switch mode power supplies and boost converters and how I might use this in this preamp project. As I say, most of my knowledge has been focused on old school, mainly tube technology, passive components, that kind of thing. So I don't have a lot of experience working with transistors and solid state devices, ICs and things like that. But it doesn't mean I don't understand them and can't understand them. I just have to do a little more research when I'm going to use them. So I'm not going to really go too heavy into an explanation of switch mode power supplies and boost converters, and there's something called a buck converter too. We'll talk about that. Switch mode power supplies utilize a switching regulator to convert electrical power more efficiently. It transfers power from DC or AC, mains wall voltage, to a DC load. Switch mode power supplies are substantially smaller and lighter than a linear traditional power supply because the transformer can be much smaller. This is because it operates at a high switching frequency. At higher frequencies, a transformer core can transfer more power without reaching saturation. This means fewer turns are needed, and it makes the transformer smaller and less costly to build as well. The topology and electromagnetic compatibility requirements of a switch mode power supply usually results in a much greater component count and corresponding circuit complexity. I'm not going to go into the theory or design of switch mode power supplies. It's beyond the scope of this video. So we'll leave it at switch mode power supplies are smaller, more efficient, and more cost effective. I also mentioned boost converter and buck converters, and those are a class of switch mode power supply. What a boost converter does, it's also called a step-up converter. It's a DC to DC converter that increases voltage while decreasing current from its input supply to its output the load. Sounds familiar. Boost converters contain at least two semiconductors, a diode and a transistor, and at least one energy storage element, a capacitor, an inductor, or the two in combination. Switching converters provide much greater power efficiency than linear regulators, which are simple circuits that dissipate power as heat. Basically, they throw away power to do the job that they do, which makes them inefficient. The efficiency of boost converters can be very high, often exceeding 90%. So very efficient, very good use of the power. To reduce ripple, you can use an RC filter on the supply side and load side. I don't think it's going to be too critical to add it on the supply side, and I'm not planning to do that, mainly because the main power is going to come from a 12-volt supply that will be external to the project, and I don't think we're going to have a lot of issues with noise. I think there's filtering on the power supply itself. On the load side of the boost converter, which will be inside the amp, I will be putting an RC filter. We'll talk about that later. Power for a DC step-up converter can come from any DC source. You can use batteries, you can use solar power, rectified AC, and or a DC generator. Buck converters step down the voltage but increase the current capability on the load side. So that's great if you have something that requires low voltage, high current. Tube amps require high voltage, low current, so I won't need to use a buck converter in this at all. It just fits with this subject. In addition to smaller transformers, higher switching frequency allows the use of smaller inductors and capacitors as well. So everything gets more compact. The only downside with the higher switching frequencies is it leads to increased switching losses in the transistors. So that can reduce efficiency. Still, most of these converters operate in the 85 to 95% efficiency range. That's incredible. That's all I'm going to talk about with this. To be honest, I haven't even really gotten into looking at the design and theory behind switch mode power supplies. If I find that this works well in this project, obviously I will probably do more research. I've only done what I need to do to sort of satisfy myself that what I've got to power this preamp circuit is going to work. So obviously, rather than the traditional power supply I detailed earlier in this series, I'm going to now be switching to switch mode power supply external and an internal boost converter. Switch mode power supplies and boost converters are available off the shelf, and they're not very expensive. For the switch mode power supply and boost converter that I got for this project, for both of them combined, I spent under $40 Canadian, definitely under $50 Canadian. So that's a darn sight cheaper than what we would build using a transformer and big filter capacitors and all of that. Mainly the transformer for a power supply, even for this preamp, can get pretty costly, pretty much double what I've paid for what I'm using now. And as I say, they're big and bulky. The switch mode power supply is going to provide 12 volts DC, and I will be using that 12 volt DC for the low voltage components in the preamp. So the pilot light LED, the edge lighting LED strip, and the heaters for the 12AX7. I also will be using that 12 volts DC to power the boost converter, which will convert that 12 volts DC to anywhere from 200 volts DC up to 450 volts DC. It's variable with a pot. This is also very cool because it lets me fine tune the voltage at the plates of the 12AX7 in the preamp here for more headroom, more clean output, or I can even bring it down, start to starve it if I were going to use this, say, for guitar purposes and get it clipping. Of course, this is a bass preamp. I'll be running the plate voltages a little higher than I would probably for a guitar amp. Right now I'm thinking somewhere in the range 260 to 300 volts DC. The maximum plate voltage for 12AX7 is 350 volts, but Fender and many other manufacturers regularly push it higher than that, 400 450 volts for a reverb driver, for example. I'm not going to push it that hard. As I say, probably somewhere between 260 and 300 volts DC on the plates. Probably for the first gain stage, I'm going to go somewhere around 260 volts, and for the second gain stage, somewhere around 290 volts. We'll play around with that and see what works best once I've got the preamp built. As I say, we can adjust the voltage independently, and that won't change the voltage to the heaters of the 12AX7. So it's sort of like a built-in power scaling feature. So along with doing all of that, now I will have much more space in the chassis. The overall design will be less complex, and it will be lighter and a little less costly to build as well. As I said, the supply power, the switch mode power supply supplying the 12 volts to the preamp will be an external, basically a laptop brick. So we don't have any issues with AC induced hum, because the only AC involved in the whole thing will be the AC going from the wall to the switch mode brick, which will not be in the amp. It can basically sit down on the floor. There can be other noise, as I've said before, due to the switching, and I will be adding some filtering, at least on the load side of the boost converter, to help deal with that. We'll talk about that more a little later in this video. A lot of this will become fleshed out more when I actually start putting the preamp together. Today I'm going to just sort of mock things up and show you how it's going to work. We'll take some measurements so we can see where we're at in terms of current draw and voltages and whatnot. I'm going to show you this and how much space we're going to save. I have the smaller chassis that I had originally planned on using. I am still going to use that 12 inch wide by what was it, probably 8-inch deep chassis, just because this is my first time using the switch mode power supplies, and if it doesn't work out, I'll want to put a traditional supply in there, and I will want the room to be able to orient things in terms of reducing AC hum and whatnot. One thing I'm kind of excited about, though, is I had not been too sure I wanted to use this transformer for the DI balanced output, because it is a transformer and it can pick up extra AC noise, and especially in this smaller chassis, I was having trouble getting things oriented in a way that would reduce the hum as much as I wanted. Now I'm not going to have that issue. So with the traditional style of power supply I had been planning on building, the transformer was going to go up here. The 12AX7 would have gone over here, and we'd have the cap can here. I would have had to have put this this 5-volt switch mode power supply. This was the main thing that prompted me to go to a larger chassis, by the way. I would have had to put it somewhere, you know, maybe over here or over on the other side of the transformer. And we also would have the big filter caps, and they would have to go in here somewhere. The circuit board itself also would be in here. Again, I couldn't sort of orient things to minimize the hum as much as I wanted. It was pretty reduced, but there was still some there. So anyway, we're looking at a pretty cramped chassis, and this is not a lot of stuff to put in here. So now I don't need this little 5-volt guy. I have to figure out something to do with that. I bought 2 of them. I do have some ideas. I am, you will see, going to need to use one electrolytic. I'm going to use a 100 microfarad. I have a F&T 100 microfarad 450 volt. Maybe a little under-spec'd if I was going to be running this at 450 volts. I'm comfortable using this in here at least for now. Obviously, I do need the tube socket. I don't need the power transformer anymore. And I don't need the can cap anymore. So here's the new chassis, and all we're going to need to squeeze in is the actual preamp circuit itself, the boost converter. That will provide all of the voltage for everything we need in the amp. I will be adding an RC filter. That can go in here on a little daughter board. I've put some wires in the boost converter so we can do some testing with it later. And the only other thing that needs to fit in there is the 12AX7, which can go up over here somewhere. So I'm able to get everything farther away from the power. It's all DC power, so I don't have to worry about AC hum being induced into the line transformer. And I have a lot more room in here. So this is going to be awesome. I'm really happy with this. As I say, the only additional thing now I have to do is just make a little daughter board for this filter capacitor. The only thing I need to have on the outside, of course excluding the controls and the input and output jacks and whatnot, is the 12AX7, which can go somewhere over here. This board will be on the inside here, and all the power and stuff can go over here. That's the plan and the thinking, and the benefit. Another benefit using these switch mode power supplies. Earlier I mentioned searching YouTube to find out what other people have done using switch mode power supplies in this sort of a project. And one of the videos, actually there's 2 that I came across, were from a guy who goes by Loon. Just his videos, his 2 videos are amazing. I will link them in the description below and maybe put a card up wherever they go. Have you ever noticed nobody knows which side the card actually ends up on? In his videos, Loon demonstrates his project. He did his own take on a Dumble steel string Singer, and he built it a separate preamp unit and power amp unit, and used switch mode power supplies for both of those. And I gotta say, the videos are impressive. The tones that he gets out of that project is just amazing, and I really like he didn't label anything, so you have to remember what knob and switch does what, but that's kind of cool. It's you'll see it if you watch the video. Also, I found a forum discussion just doing some searches, which turned out to be a forum discussion led by him on this project, and he did actually link to that forum on his 2 videos as well. But I found them before I found the videos. Actually, I found the videos from reading the forum. On the forum discussion, he goes by JHJH217. So YouTube at Loon and LOON, and on the forum discussion, JHJH217 is him. And in that forum discussion, he had included his email address for somebody else who was asking him questions, and I thought, oh, I'll email him because he done all of this about a year ago, and I want to get an idea of how the project held up. He got back to me very quickly. It was over the Christmas break. So I'm just going to read this. I saw your video and it looks great. I really like that it features a balanced output. My preamp is holding up very well. I gigged regularly throughout the year, had more than 100 hours of live use, and it has worked flawlessly. My preamp uses 550 milliamps at 12 volts, and I'm using a pedal power supply. He's using a Chuck Sol. He says, for your preamp, it will use less current since it's a single valve preamp. And he says, switch mode power supply should work definitely for my project, and it should be no issue. So, and I had already kind of decided that. I'd already ordered the parts by the time I emailed him, and he got back to me. He says, even though switch mode power supplies DC power, it isn't very clean. Switch mode power supplies have a real reputation for being very noisy, and that's mostly from the early days in the 70s and 80s. It's a lot better now, but there is still noise you can get. I have seen some guys who have done this and they didn't use filtering, but I agree with him. Filtering it, we want this as quiet as possible. He says much less filtering is needed compared to a linear power supply. He says, I use second order low pass filtering with a cutoff frequency of 2 to 3 hertz to achieve dead quiet preamp. He says just a single low-pass filter should be sufficient. In his video, Loon shows the schematic for his power amp, and he used a 150 ohm resistor with a 68 microfarad capacitor RC filter, and doing the calculation, that has about a 15 hertz cutoff frequency. He says he got down in his email to me to 2 to 3, so I did some playing around, and using an online low-pass filter calculator and playing around with numbers. If I use an 820 ohm resistor and a 100 microfarad capacitor, as I showed you earlier, I will get right at 2 hertz cutoff frequency. So should be very quiet. So that's the route I'm going to go with this. Again, if things aren't right, I can tweak and adjust in testing. Since the voltage of the output converter can go up to 450 volts. If I thought I was going to go that high in terms of my usage, I would want a electrolytic rated at 500 volts or more. I have no intention of dialing it that high, and anybody who goes in there after me should not, for obvious reasons. So the highest I expect this would ever go in terms of voltage would be 350 volts, and like I say, I'm going to keep it 300 volts or under. So I think I'm good with that 450 volt capacitor that I'm planning on using. He says things that could be beneficial. So he made some suggestions. He said, unbalanced output will have a very hot signal level. Yes, this is supposed to be a line level output unit, which will go direct to a recording console or another power amp or something like that. He says, if you're planning to use it with other pedals, reverb pedals, etc., I'm not. And I know my brother would use pedals in front if he used pedals at all with this. He says you might want to add a voltage divider circuit with an on-off switch so you could attenuate the output level to instrument level or line level and then use it with pedals. That's a really good idea. And I might do that. He says without the switch, you could just use the volume knob and attenuate, just bring the volume knob down low enough that you're not clipping the guitar pedal, and this will apply to guitar pedals. Line level effects won't have a problem. I might decide to install a pad switch to attenuate it for pedals, but it's the kind of thing, if I don't put it in now, it can always be added later easily. So we're going to get back on the desk, and I'll show you the components. We'll do some tests and see where things are at. Here's the power supply brick. Can take 100 to 240 volt AC input, 50 to 60 hertz, and it can output 12 volts DC with a capacity of 5 amps. So it's tip positive. I do have it plugged in on my wall voltage monitor here, and it is already wired up to my breadboard. I can turn this on. Well, first of all, I'll tell you what we got happening at the wall. With just the supply plugged in and running, we have no load on it. We're not drawing anything in terms of wattage out of the wall. No, nothing amps wise out of the wall. Today, the wall voltage is 123.2 volts, so a little bit high, but it's usually around there. I've wired my old fluke meter to monitor the current, so it's in series with the supply. It's on the positive rail. And I've also wired my other meter across the voltage input just so we can monitor the input voltage as we're doing tests here. So with no load or anything, we're getting 12.14 volts DC. It's really stable. It's going between 12.14 and 12.15. Current wise, I'm monitoring, and it's down at 0. This is my old fluke meter, and all the buttons have gone. So to switch it, I got to use a screwdriver. Let's go take a look. We'll put this on the 2 milliamp scale and see what we're getting there. Yeah, on the 2 milliamp scale, we're way down 0.02. What is that? Microamps? Yeah, like we're way down. Just a very minor amount of current is being drawn right now. I'm going to take this back up to the 2 amp scale. That's the switch mode power supply. 100 to 200 volt AC in, 50 to 60 hertz. 1.5 amp current draw from the wall. Output 12 volt DC and can take up to 5 amp current pull. So the next thing is the indicator LED pilot lamp. It says it can take 3 to 9 volts DC and 20 milliamps current. I measured it. I put it on a 9 volt battery. At 9 volts, it was drawing 15 milliamps. So you could probably push this to 12 volts, like I'm using here, but it's already very bright. So I'm not going to push that. I've got a resistor in series with it to bring the voltage to it down and dim the light a little bit and make sure we're in a good current range. It seems to be bi-directional. It doesn't really care which way I provide power. They say that the power should be positive should be to the green wire, but if I put positive to black and green to negative, it still lights anyway. So I think it's a bi-directional LED. Since it's orange, it looks more yellow, but they say it's orange. So since it's orange, the forward voltage for an orange LED is 1.7 to 2.4 volts. So I'm assuming 2 volts forward voltage on this. I'm also assuming that there is a resistor built in here to limit the current. So there's probably a resistor in there. It's just to keep this from burning out. I don't know that, but based on the testing, that's what I suspect. So using the formula to calculate the value of the possible built-in resistor, the calculation is the LED resistor equals the supply voltage minus the forward voltage divided by the forward current. So supply voltage 9 volts. If the forward voltage is 2 volts, that leaves us 7 volts to drop with a resistor. The current, as I measured, was 15 milliamps. So putting that into the calculation, the resistor equals 9 minus 2, 7, divided by 15 milliamps, or 0.015 amps. So I suspect there's about a 460 ohm resistor in here as well. I might be wrong. I don't know. Specs, you can't really get specs for these. The specs I did get, I did a lot of searching for, and I'm trusting they're correct. In terms of the LED lighting, as long as you give it enough voltage, it will light with very low current. So you adjust your current. You don't want to go over what the forward current is because you'll burn it out. But you can go very, very low depending if it's too bright or not. So you've got a lot of leeway. Since I'm using a 12 volt DC supply and the LED is rated for 9, I'm going to I want to put an additional resistor in series to limit the current, and I have done that. I sort of made a best guess using to figure out the additional resistor. I took the supply voltage, 12 volts, minus the voltage we want the LED unit to see, which is 9 volts. And divide it by the forward current, which I measured at 15 milliamps. So taking a supply voltage 12 volts, the LED voltage at 9 volts, and the current that we measured of 15 milliamps, we get 12 minus 9, or 3 volts, divided by 0.015 amps, or 15 milliamps, and that suggests adding a 200 ohm resistor, which I did add. So that would give us, the resistor power rating would need to be about 0.045 watts. So I'm using a 1/4 watt resistor, so well over spec. Let's actually plug this in and see what happens. So we've got our LED. It's lit up. It's drawing exactly 15 milliamps. So bang on. So we nailed that one pretty well. I'm not going to measure what the voltage is to the LED itself. I'm pretty confident it's about 9 volts. Our numbers are so close. I would bet money that that's at 9 volts. So that's the indicator LED. Let's move on to the strip for the edge lighting. I'm not using the LED strip I showed in the last video. That was the 5-volt strip. This is a 12-volt LED rope, they call it. It takes 12 volts DC. The strip length itself is 16.4 feet, or 5 meters, so way more than I need. But it has 300 LEDs total in that length, so not quite as tightly packed. And it can be cut every 3 LEDs, or about every 2 inches. So groups of 3 LEDs, and to go 12 inches, I need 6 of the groups. I'm assuming that they are powering this 5 milliamps per LED, based on the specifications of the rope, which says 1 to 2 amp total for the 5 meter length. So I chose 1.5 amps, based my calculations on that, and that comes out to 5 milliamps per LED, or a total of 900 milliamp draw. So that's the theoreticals of it. I'm going to plug this in, and we'll measure and see what we really get. There is a resistor in each group here too. It's too small for me to read. It's a little surface mount device, but if I recall, it's a 330 ohm resistor. I've connected the LED strip. Now I'm going to turn the power on, and you're going to see, you'll hear the click, and there'll be a lag before the light goes on, and that's going to be important when we get to talking about the tube heaters. So here we go. We'll turn this on, listen for the click, and watch how long it takes for the LEDs to light up. It'll take not too long, but there will be a brief instant where it doesn't come on. So, and there you go. So that actually was, I think, pretty close to a second before it was providing enough power to light the LEDs. So what do we have? We have our voltage is dropped down to 11.82 volts. That's still close enough to 12 volts. There will be voltage drop because now we have a load. And what are we pulling for current? We're pulling 95 milliamps. So bang on. As I say, the wall is providing just a little under 124 volts today. So that accounts for the extra 4 or 5 milliamps we are seeing here. But that's bang on. So far the calculations are working out really well. 15 milliamps for the pilot light. We're drawing 90 milliamps for the strip light. The other low voltage component, I'll call it, that is going to be powered by this 12 volt supply is the heaters in the 12AX7. I've got a 12AX7 here, and I've wired it up with some alligator clips. The 12 and 12AX7 is for 12 volts for the heaters. And you might be saying, well, why does every amp have a 6.3 volt heater supply? And that's because the way most amps wire the 12AX7, they're wiring the heaters in parallel. Each filament, there are 2, it's a dual triode, a 12AX7, needs 6.3 volts. So when you connect them in series, you need a total of 12 volts, 12.6 volts actually, but 12 volts is close enough. So to run those in series, you connect to pin 4 and pin 5, you don't connect anything to pin 9, and then you have your heaters in series. One thing that I was concerned about using the switch mode power supply is inrush current. So What the inrush current is, when you start a tube up from cold, in other words, the amp's been turned off for some time, several hours, days, weeks, whatever, the filaments are cold. When they're cold, the resistance is lower than they are at operating temperature when the filaments heat up. That lower resistance causes it to draw more current than it will sit at when it's operating. Providing 6.3 volts to parallel filaments on a 12AX7, you'll get a 300 milliamp current draw. Running them in series like this at 12 volts, similar to running 120 volts or converting to 240 volts, your amperage requirement drops, your current requirement drops. So running these in series, it wants 150 milliamps. But when you start it cold, the current can spike up quite a bit higher than that, around up to around 8 times the current that it would be at its regular operating temperature. So that means the current could spike up to as much as 1.2, maybe even as high as 1.5 amps. So I was a little concerned about that and was keeping an eye on that in case I needed to do something about it. You can do things to limit that inrush current. Fortunately, I don't have to, because this switch mode power supply, whether by intentional design or just happy coincidence, seems to have a soft start. It doesn't provide all the power immediately when you turn it on. You connect the power and there's a little lag before the light turns on, and that's what you would consider a soft start. It doesn't provide the current right away. So we're going to turn this on. I've got this set to the 2 amp scale just in case we do go over 200 milliamps, and I think we will on the initial draw here. But I don't think we're going to go too much higher over that. We might be, but it might be so brief. As you saw, that only took a second for everything to come on. So if we are spiking higher than that, we're really probably not going to catch it here. But I don't think we are. So when I turn this on, you'll hear the click. Watch in particular the ammeter, the current reading here, to see if you can catch where it spikes up to. So here we go. Okay, so it's still settling down. I saw that shoot up to 400 milliamps. So we're definitely getting there. I wouldn't have a problem believing we might be shooting up to 1 amp. At the end of the day, we're not really drawing more than this supply can deal with anyway. So I'm not going to worry about any sort of inrush current. So what have we settled at? We're at 11.7 volts here, again, because we are drawing current, so it has dropped a little, the voltage a little bit. It's still basically 12 volts. We're drawing 135 milliamps, close enough to the 150 milliamps we expect. This is all working well. We have 5 amps that we can draw out of this supply before we have a problem, and we're well below that. If I look what we've got, even if the pilot light creeped up to drawing 20 milliamps, we got 90 milliamps for the LED strip and 150 milliamps for the heaters once everything settles. That's only a total 260 milliamp draw. At startup, if we're spiking at all, we're somewhere around 1 amp. We have 5 amps available on this supply. So once this all settles back, we could still draw another 4.74 amps when we get the boost converter and the preamp circuitry. So let's just look at what we've got right now, excluding the boost converter. I'm going to turn this off. I'm going to wire the pilot light back in, wire back in the LED strip. I'll leave the heaters for the tube in. This is all of the low voltage devices, excluding the boost converter, because we're gonna look at that separately. Doing the math, we expect to see somewhere around 255 milliamps when everything settles, and our voltage should still be around 11.5 volts. I'll turn this on. Watch the meters again just to see what happens. See how high our amperage might spike up here. So listen for the click and watch the amps. It only went up to like 412 milliamps. So everything's on. We're at just a little under 11.5 volts supply. Still good, no problem, no worries. And we're drawing 237 milliamps. So what did I estimate? 260 milliamps. We're about 24 milliamps under that. So good. We've got lots of amperage left for when we put the boost converter in here.